Okay, so in the next two videos, we're going to be looking at the process of fatty acid synthesis. I've broken this up into two videos because the first video we're going to examine the delivery of substrates for the synthesis of fatty acids. And then the second video we will look at the reactions that are being performed in order to generate the fatty acid from the substrates we've delivered in this video. Now, in order to fully examine fatty acid synthesis, we need to consider the physiological conditions. We are going to focus on the liver. And in the liver is the major source of fatty acid synthesis in the body. Now, because this fatty acid synthesis, the fatty acids, are large molecules, it is going to take an enormous amount of energy to generate these large molecular structures that harbor a lot of energy for later use. And so these reactions will be occurring in an anabolic state. So recall that in an anabolic state, we are in a fed state where we have high glucose levels because we've just eaten. So this is the fed state, and that also results in a high insulin hormone circulation in the bloodstream. Now, let's take a look at the process of how the liver is functioning to process the glucose, as we've seen before. So the first response, of course, is because the concentration of glucose is high, the liver will be able to take the glucose up into the cytoplasm through the GLUT2 transporter. The first reaction is to phosphorylate the glucose into glucose 6-phosphate, of course, by glucokinase. Recall the glucokinase is paired with the low affinity transporter GLUT2. Now, the glucose 6-phosphate can be processed through glycolysis with its end product being pyruvate, generating energy. The other two pathways that we can have, of course, in the liver is to take the glucose 6-phosphate and use this to synthesize glycogen. And of course, this glycogen, the glucose stores in the liver, are for the fasting state. The other pathway that we can take with glucose 6-phosphate is the pentose phosphate pathway. Now recall the pentose phosphate pathway is generating two important substrates. One is NADPH, which is going to be an important reducing source for generating fatty acids, and also ribose sugars, so that we can produce nucleic acids and nucleotides. Now, once the pyruvate is generated, this will enter the mitochondria through the pyruvate translocase transporter. And once we are in the mitochondria, we are going to be generating acetyl-CoA by the PDH, pyruvate dehydrogenase enzyme. Now, once the acetyl-CoA is formed, we will now take oxaloacetate and we will perform our condensation reaction in order to form citrate. This reaction is, of course, generated by the enzyme citrate synthase. And recall, this reaction is not reversible because this is a very large negative delta G because of the hydrolysis of this thiol ester and the acetyl-CoA to drive this reaction. So now this is, of course, the first step in our TCA cycle. After citrate, we form isocitrate. This is an important reaction in generating the substrates for fatty acid synthesis because of the reversibility of this enzyme. This enzyme, of course, is aconitase. The aconitase being reversible will allow us to take isocitrate and return it to citrate. Now, under what conditions will those happen? Well, recall, after the isocitrate reaction, we have alpha-ketoglutarate. this reaction is performed by the isocitrate dehydrogenase enzyme. Now, important to remember about this dehydrogenase enzyme is that this is a redox reaction to generate NADH. Because we are in a fed state, we have lots of glucose being oxidized. We have lots of substrates coming down here to generate a very high concentration of NADH in the matrix of the mitochondria. This will feed back and inhibit this enzyme. By inhibiting this enzyme, we are preventing the conversion of isocitrate to alpha-ketoglutarate. Now, this reaction is important to block this reaction here because it is not reversible. So let's inhibit this enzyme, and then as a consequence, we are going to increase the concentration of isocitrate. Now, this is where the reversibility of aconitase is very important. As the isocitrate concentration builds up, we have a change in direction of aconitase activity. So now that the reverse direction becomes the negative free energy reaction. What that will essentially do now is return the isocitrate to the citrate and increase the concentration of citrate in the matrix of the mitochondria. Now, the reverse reaction to regenerate acetyl-CoA and oxaloacetate is not going to happen because this is not a reversible reaction because of the hydrolysis of this thiol ester. This is a very high energy bond, and it drives the reaction forward to make it irreversible. So that means that we have to have a path for citrate to exit the reaction in order to keep the reversibility of isocitrate going. Now, what we are going to do with this reaction is we are going to send the citrate into the cytoplasm. So this is our inner mitochondrial membrane. So we have a transporter that is going to transport citrate into the cytoplasm. Now notice the way I've drawn this transporter. This is an antiporter. So that means we're going to transport citrate out and another molecule in. We'll take a look at what that is in a few minutes. Now, once we have the citrate transported out into the cytoplasm, let me draw the structure of citrate. So here is citrate. Now the next reaction we are going to perform is we are going to generate acetyl-CoA in the cytoplasm, and we are going to generate oxaloacetate. Now the oxaloacetate is going to have a fate of its own. The acetyl-CoA will go on to be the substrate for fatty acid synthesis. And we'll take a look at this in the next video. The oxaloacetate obviously needs to be returned to the matrix of the mitochondria. So the enzyme that's performing this reaction is called citrate lyase. Citrate lyase, we are simply breaking, a lyase means we're breaking a carbon-carbon double bond. Specifically, we are breaking this bond to generate the acetyl group with CoA added to the reaction. Now, the reason we need to return oxaloacetate to the matrix of the mitochondria is because we are transporting important carbon sources out of the matrix into the cytoplasm simply to deliver the acetyl-CoA into the cytoplasm for fatty acid synthesis. So the citrate is essentially a carrier of acetyl-CoA. This means that the remaining portion of the carbons we need to return to the matrix of the mitochondria, so notice back here we can continue the condensation of acetyl-CoA with oxaloacetate to generate more citrate to keep the cycle going. So the next step of this reaction of oxaloacetate is we are going to convert this to malate. Now, the enzyme that does this is called malate dehydrogenase. Now, recall that in the TCA cycle, we are also forming oxaloacetate from malate. The enzyme that performs this reaction is also called malate dehydrogenase. There are two forms of this enzyme. One is in the matrix of the mitochondria, the other is in the cytoplasm. Both of them perform the same reaction, which is a redox reaction. Now recall that if we are going to be performing a redox reaction, we need a redox cofactor partner, and this is going to be NADH. So we are going to use NADH and the cytosolic malate dehydrogenase to convert oxaloacetate to reduce it into malate. Now, where does this NADH come from? Recall, NADH cannot be transported from the matrix of the mitochondria into the cytoplasm. So the NADH needs to be generated in the cytoplasm. Integration of pathways is the answer. Here we have an anabolic fed state in the liver. We have glucose coming into the glycolytic pathway, and at the point of the glyceraldehyde 3-phosphate dehydrogenase reaction, we are generating NADH. So this NADH is coming from glycolysis. This is being continually generated because we are in a fed state, which means we have plenty of glucose feeding the glycolytic pathway. Now malate, once we form malate in the cytoplasm, it has two directions it can go. The first direction is that the malate can now be transported back in to the matrix of the mitochondria. Thus, this shuttle system, this antiporter, is called the citrate malate transporter. So the antiporter activity is bringing the carbon source citrate, which is the carrier of acetyl-CoA, out into the cytoplasm, and malate is returning into the matrix of the mitochondria so it can be oxidized into oxaloacetate. So this reaction is performing two essential functions. First of all, we are returning the carbon sources that we delivered the acetyl-CoA into the cytoplasm back into the matrix. And second, we are taking some of this NADH being generated from glycolysis and delivering it to the matrix of the mitochondria to return it malate to oxaloacetate. By shuttling these electrons into the matrix of the mitochondria, we can generate the NADH back again after using it in the cytoplasm in the matrix of the mitochondria, and then use that NADH to generate energy. So again, this is an important reaction because NADH does not have a transport capability across the inner mitochondrial membrane. So in order to get this reducing equivalent into the matrix of the mitochondria to use it for energy, we need to use either this particular malate shuttle, or recall we looked at the glycerol 3-phosphate shuttle in an earlier video when we examined the electron transport chain. Okay, now going back to the malate, one direction the malate can take, as we said, is using the citrate malate transporter to be returned to the matrix of the mitochondria. The other path that this can take is to form pyruvate. Now this pyruvate is being generated in the cytoplasm. The enzyme that does this is called the malic enzyme. The purpose of this particular reaction is to generate more NADPH. Now in order to generate this energy, we are also needing the electrons. And so the electrons that we are going to be taking from this particular molecule are going to be a carbon-carbon bond break, and that is generating CO2. So this is an oxidative decarboxylation reaction. We're taking a 4-carbon, generating a 3. Now we are losing energy from this molecule by converting it from a 4-carbon to 3-carbon and losing the CO2, but we are transferring that energy into a different form, and that's form of NADPH. The NADPH, of course, will be essential for the reactions to generate fatty acids in the reaction sequence of fatty acid synthesis. Now once we generate the pyruvate, recall we have the pyruvate translocase that operates by proton gradient. This is our pyruvate translocase, and this is of course a symporter, secondary active transport using the power of the proton gradient. Now the question becomes, is when does malate take path 1 versus path 2? This decision-making point will be largely based on the concentration of NADPH. So recall that the majority of NADPH is being made by the pentose phosphate pathway. Back up here, our first reaction is the glucose 6-phosphate dehydrogenase to generate NADPH. This pentose phosphate pathway is the major producer of NADPH. The malic enzyme bypass is a secondary source of NADPH because so much of it is going to be used into fatty acid synthesis. We want to make sure that we are not limited by this reducing power to generate the fatty acids. So path number 2 will be dictated by NADPH levels. So if these levels start becoming low because of intensive fatty acid synthesis, then we are going to be shuttling our malate into pyruvate to restore this. If our levels are still high because of much activity in pentose phosphate pathway, then the malic enzyme will be inhibited by high levels of NADPH, and path 1 for malate going through the citrate malate transporter will be preferred. So the other way to look at this is that this is the default pathway. Malate will generally go through the citrate malate transporter unless NADPH levels are low. Now in the next video, we will take up the process of acetyl-CoA being converted into fatty acids.